A very warm welcome to all. This is Maulika, Assistant Professor, Department of Physics from St.Josephs College of Arts and Science for Women, Hosur. In this video, I am going to explain about Langevins' theory of diamagnetism. Basically, we have five types of magnetic materials. We know that one is diamagnetic material, second one is paramagnetic material, then the third type is ferromagnetic material, and the fourth one antiferromagnetic material, and the fifth one ferrimagnetic materials. First of all, what is meant by diamagnetic material? Which diamagnetic substances are those which are feebly repelled by the magnet. For example, antimony, bismuth, copper, gold, these are the diamagnetic materials. In this session, I am going to explain about classical theory of diamagnetic materials. This theory was given by Langevins. So we can say this theory also Langevins theory of diamagnetism. This theory proves the property of the susceptibility of the diamagnetic material is always negative and it is independent of its temperature. Consider an electron of mass m, the charge is E. So the electron rotating about the nucleus of charge is at E in a circular orbit. The radius of the orbit is r. Let omega naught be the angular velocity of the electron. Then the first condition is let a magnetic field of induction B is not applied. That time, two forces are acting in it. Both are equal, which is centrifugal force and Coulomb force. We know that the formula for centrifugal force is mv squared by r, and the Coulomb force is 1 by 4 pi epsilon naught q1 q2 upon r square. Now, the second condition is we are going to apply the magnetic field of induction to the electron. So, that time the additional force, Lorentz force, acts on the electron. The value of the Lorentz force is minus EB or omega. Okay. The condition of stable motion is given by the value of centrifugal force is equal to the difference of the Coulomb force and the Lorentz force. Using quadratic equation, we can get the angular frequency value with the magnetic field applied to the electron. That means second condition. The answer is the plus or minus the square root of omega naught square plus EB upon 2m the whole square minus EB upon 2m. In this term, EB upon 2m referred as Larmor's frequency. This Larmor frequency is very small compared to the natural frequency. So we can neglect this term. So we can get plus or minus omega naught minus EB by 2m. So the change in angular velocity of revolution of the electron is the difference of angular velocity with applied field into without applied field. So the answer is minus EB upon 4 pi m. So now the change in we are going to calculate now the change in magnetic moment of the electron, that is current into area. We know that area of the circular orbit is the pi r square, no? Then the current value is, we can get normal equation I is equal to q by t. So the value is minus b e square r square upon 4m. On summing overall electrons in the atom, the induced moments per atom becomes minus b e square epsilon r square upon 4m here, and the net magnetization is given by minus n b e square summation of r square by 4m. Here n be the number of atoms per unit volume. All the electron orbits are not oriented normal to the magnetic field. Hence, R square in the above equation, that means the last equation, should be replaced by the average of square of the projection of the orbit ready for various electrons in a plane perpendicular to magnetic field. So now we are going to substitute, instead of r square, 2 pi 3 r square value. After that we can get the magnetic moment value is minus nbe square summation of r square upon 6m. Now, our ultimate aim is finding the susceptibility of the diamagnetic material. So, we know that the formula of volume susceptibility of the material is magnetic moment by magnetic field strength. So, the final value, we are getting minus n mu naught e square summation r square by 6m. We can notice the minus value are presenting here. It means the susceptibility is negative and there is no temperature term present. So we can say the diamagnetic materials, the susceptibility of the diamagnetic material is always negative and it is independent of its temperature. So this is about the Langevins theory of diamagnetic materials. Thank you.